Salam and greetings. My name is Muhammad Aiman bin Muhammad Roslan, matrix number KIB190030. Today we will be conducting an RLC circuit experiment using the TINA software by Texas Industries. Firstly, we will be studying an RC circuit. This circuit consists of a voltage R1, capacitor, another resistor R10, and is connected to the ground. Once we place the components, we will connect it with the wire like so. Then two voltage pins will be placed as such, one after R1 and another after C1, so that we can obtain a reading using the oscilloscope. For the voltage source, we will be using unit step to simulate using an AC generator with amplitude of 1 and DC level of 0. Next, we must insert the value of the components. For R1, we'll be using 2k ohm, and for C1, we'll be using 2 microfarad. Note that we only need to type in the value without the unit. And then for R sense, we'll be using 1 ohm. Note that R sense is placed so that we can obtain the reading of current from the oscilloscope. Now, we will observe the waveform of the circuit using the oscilloscope. We can adjust the axis so that we can view the waveform better. Note that for unit step, we will have to change the mode to single. Now, note that at VF1, the green line, which is after the resistor, the voltage increases until it reaches a steady state. This shows that it is directly proportional with the voltage supplied by unit step. Note that at VF2, which is the red one after the capacitor, the voltage decreases until it reaches a steady state. We can assume that with the decrease of voltage, that the current is increasing steadily until it is steady, which shows that the capacitor is being charged by the voltage supplied. For the second part, we'll be studying an RL circuit. The circuit is similar to the previous one, only the capacitor is replaced with an inductor. The configuration of the component is the same, so is the value for R1 and R sense. For the inductor, we will be using 2 mH. However, for RL circuit, we will be changing it to an AC source or sinusoidal wave with an amplitude of 0 and a frequency of 50 Hz. Again, now we will observe the waveform using the oscilloscope, but now we will be using normal or automatic mode. Again, we will adjust the axis until we can observe the waveform properly. Now, note that both VF1 and VF2 will produce sine waves, but they appear slightly shifted. From what we learned, we can calculate the phase shift between the two waves by obtaining two readings from each curve that are at the same phase. Here, I will choose the readings of the curve in the first row. Once we obtain the readings in milliseconds as XA and XB, we can transfer it to an Excel sheet where we can calculate the phase shift. Here, we have XA, which is 4.69 milliseconds, and XB, which is 6.14 milliseconds. Now, Now, using the Excel formula, we can obtain the T difference between XA and XB. We can also obtain the period, which is 1 divided by frequency, where we have used the frequency 50 Hz. We get the period of 0.02 seconds. Finally, we can get the phase shift in degrees by multiplying 360 degrees with the division of time difference over the period of oscillation. To change to radians, substitute the 360 degrees for the equivalent of 2 pi in radians. For the third part, we are studying an RLC circuit. For this circuit, we will have the resistor, the inductor, and the capacitor in that order in series. For R1, we'll be using the same value of 2000 ohm. For L1, 2 microhenry, and for the C1, we'll use 2 microfarad. Now, the voltage pins for this circuit will be placed after each resistor, inductor, and capacitor, so that we can observe the waveforms after passing through each component. Now, by using the oscilloscope, we can observe that the waveform for VF1 and VF2 are synchronized, which means there is no phase shift between the two waves. However, for VF3, you can see that it is slightly shifted. Again, we can obtain the values two values from each of the curves, which are in the same phase, so we can calculate the phase shift. Here again, we will get the values as XA and XB. And again, we can transfer it to the Excel sheet where we can calculate the T difference, and from there we can get the period from the frequency, and we can, using the same formula, we will get the phase shift in degree and in radians. Lastly, I would like to show you the effects of changing the frequency on the voltage source to a circuit waveform. We will change it from 50 Hz to 25 Hz, reducing the frequency. Now we can theorize that with the reduction of frequency, that the period of oscillation to complete one entire sine wave increases. So by using the same same axis in the oscilloscope, we will see less waves being completed within the view of the oscilloscope. As you can see earlier, if we compare that there are more waves in the field of view, where now there is only one complete wave. But again, as you can see, the VF1 and VF2 are synchronized, while VF3 is still has a phase shift. So that is all from me. Thank you.